According to a recent study, the Earth's inner core is spinning in reverse.
Right now, as you're watching this video, something terrifying is happening. Every second that passes, every breath you take, every photon of light streaming from your screen into your eyes is pushing our universe one step closer to its ultimate doom. Not in billions of years, not in trillions of years, but in a time span so incomprehensibly vast that the entire history of everything you know, from the violent birth of the Big Bang to this very moment of cosmic awareness, is less than a single heartbeat compared to the eternal darkness that awaits. What I'm about to tell you will fundamentally change how you see reality itself. Because while you're living your life, worrying about tomorrow, planning for next year, making decisions about your future, the universe has already begun its final countdown. A countdown not to an explosion, not to a catastrophic collision, not to any dramatic ending that Hollywood could imagine. No, the universe is counting down to something far more haunting. Absolute silence, perfect stillness, and a cold so complete that even the concept of temperature becomes meaningless. This is the story of the heat death of everything, the most certain prediction science has ever made, and perhaps the most beautiful and terrifying truth about existence itself. It's a story that begins with the fundamental laws of physics discovered in dingy 19th century laboratories, leads through the most cutting-edge discoveries of modern cosmology, and ends in a future so distant that numbers lose their meaning and time itself becomes irrelevant. But here's what will haunt you. This isn't just a story about the distant future. This is a story about right now. The heat death isn't waiting for us in some unimaginably remote tomorrow. It started 13.8 billion years ago at the moment of the Big Bang, and it's been accelerating ever since. Every star that's ever died, every galaxy that's ever faded, every particle that's ever decayed, they're all evidence that the universe's greatest catastrophe isn't coming. It's already here. By the time you finish watching this video, you'll understand why every physicist who truly grasps these implications experiences what can only be described as cosmic vertigo, the dizzying realization that we exist in a universe that is simultaneously the most magnificent and most doomed system ever discovered. You'll learn why the second law of thermodynamics is called the most depressing law in physics, why even black holes aren't immortal, and why the very atoms in your body are living on borrowed time. But you'll also discover something profound, that understanding the heat death doesn't diminish the beauty of existence. It reveals why every moment of consciousness, every spark of complexity, every instance of love and creativity and wonder is not just precious, but miraculous. Because in a universe destined for maximum entropy, the fact that anything organized enough to contemplate its own fate could ever exist is perhaps the greatest miracle of all. The year was 1824, and Carnot was obsessed with steam engines, not because he loved locomotives or factory machinery, but because he wanted to understand something fundamental about the nature of work, heat, and efficiency. His investigation into these mundane industrial devices would accidentally uncover the universe's death sentence. Carnot noticed something peculiar. No heat engine could be perfectly efficient. No matter how cleverly designed, some energy always escaped as waste heat. This wasn't just an engineering limitation. It seemed to be a fundamental law of nature. Heat always flowed from hot objects to cold objects, never the reverse. And in the process, something was always lost, something was always degraded, something was always moving from order toward disorder. What Carnot had discovered was the first hint of what would become known as the second law of thermodynamics, the law that would eventually reveal the universe's ultimate fate. But it would take another generation of physicists to understand the full implications of his work. In 1850, Rudolf Clausius, a German physicist working on similar problems, made the connection that would change everything. He realized that Carnot's observations weren't just about steam engines. They were about reality itself. Every physical process in the universe, from the smallest atomic interaction to the largest stellar explosion, followed the same relentless pattern. Energy always flowed from organized forms to disorganized forms, from useful configurations to useless ones, from order to chaos. Clausius gave this universal tendency toward disorder a name, entropy, and he proposed what became known as the second law of thermodynamics. The entropy of an isolated system never decreases. In the universe as a whole, the ultimate isolated system, entropy can only increase, always, without exception, without respite, without hope of reversal. To understand why this law spells doom for everything, we need to understand what entropy really is. Most people think of entropy as disorder, but that's not quite right. Entropy is better understood as a measure of how many ways the energy in a system can be arranged. Imagine a deck of cards. When the deck is perfectly ordered, all hearts together, all diamonds together, all spades together, all clubs together, there's only one way to arrange the cards to achieve this state. This is low entropy. But if you shuffle the deck randomly, there are trillions upon trillions of different ways the cards could be arranged. This is high entropy. Now imagine that you're not just dealing with 52 cards, but with every particle in the universe, every proton, every neutron, every electron, every photon. The number of possible arrangements becomes so astronomically large that it defies human comprehension. And the second law of thermodynamics tells us that the universe is constantly shuffling itself toward the arrangements that have the most possibilities, toward maximum entropy. This is why your bedroom becomes messy over time. This is why ice melts in warm water. This is why hot coffee cools down to room temperature. This is why every star eventually burns out. And this is why the universe as a whole is doomed to reach a state of perfect, uniform, lifeless equilibrium. But entropy is more than just a tendency toward disorder. It's also intimately connected to time itself. In fact, entropy is the reason we experience time as flowing from past to future rather than the reverse. We remember the past because it was a state of lower entropy. We can't remember the future because it's a state of higher entropy. The arrow of time is the arrow of increasing entropy. This means that the heat death isn't just the end of complexity and life. It's potentially the end of time itself. When the universe reaches maximum entropy, when every possible microscopic arrangement has been explored, when perfect equilibrium has been achieved, time may lose all meaning. Past and future may become indistinguishable. The universe may enter a state where nothing can ever change again, because change requires entropy gradients, and in the final state, no gradients will remain. The true power of entropy wasn't understood until Ludwig Boltzmann revolutionized our understanding of thermodynamics in the late 19th century. Boltzmann realized that entropy wasn't just an abstract concept. It was a statistical phenomenon that could be calculated precisely using the tools of mathematics and probability. Boltzmann's insight was this: entropy is proportional to the logarithm of the number of microscopic arrangements, or microstates, that correspond to a given macroscopic state. His famous equation, S equals K log W, where S is entropy, K is Boltzmann's constant, and W is the number of possible microstates, is now carved on his tombstone in Vienna. What this means is that entropy is fundamentally about probability. High entropy states aren't just more disorganized. They're more probable because there are vastly more ways to achieve them. When you drop a sugar cube into coffee, it dissolves not because nature prefers dissolved sugar, but because there are trillions of times more ways to arrange sugar molecules randomly throughout the coffee than to keep them all clustered together in a cube. This probabilistic understanding of entropy reveals why the second law is so absolute. It's not that entropy can never decrease, it's that entropy decreases are so improbably that they essentially never happen in practice. The probability of your coffee spontaneously unmixing itself, with all the sugar molecules migrating back into a perfect cube, is not zero, but it's so close to zero that you could wait longer than the age of the universe and never see it happen. Boltzmann's work also revealed the deep connection between thermodynamics and information theory. Each microstate of a system corresponds to a specific arrangement of information about the positions and velocities of particles. High entropy means high information content. More bits are required to specify exactly which of the many possible arrangements the system is in. Low entropy means low information content. Fewer bits are needed because there are fewer possibilities to choose from. This connection between entropy and information has profound implications for the heat death. When the universe reaches maximum entropy, it will also reach maximum information content. Every bit of information that could possibly exist will exist. The universe will become a vast, perfectly random collection of data, with no compression possible, no patterns remaining, no further information that could be added. The first scientist to fully grasp the cosmic implications of thermodynamics was William Thomson, later known as Lord Kelvin. In 1852, just 2 years after Clausius formulated the second law, Kelvin published a paper with the ominous title, "On a Universal Tendency in Nature to the Dissipation of Mechanical Energy." Kelvin's reasoning was ruthless in its logic. If the second law applied to the universe as a whole, and there was no reason to think it didn't, then the universe was doomed to what he called heat death. All forms of energy would eventually be converted to heat, and all heat would eventually be distributed uniformly throughout space. No temperature differences would remain to drive any kind of work. No motion would be possible except for the random thermal motion of particles. All life would cease. All complexity would vanish. The universe would reach a state of perfect, eternal stasis. The result would inevitably be a state of universal rest and death. Kelvin wrote, "If the universe were finite and left to obey existing laws." Kelvin's vision was so bleak that many of his contemporaries refused to accept it. Surely, they argued, there must be some escape clause, some loophole in the laws of physics that would prevent such a catastrophic ending. Perhaps energy could somehow be recycled. Perhaps new sources of energy would be discovered. Perhaps the laws of thermodynamics didn't apply on cosmic scales. But Kelvin was unmoved by these objections. The mathematics was clear. The experimental evidence was overwhelming. The second law of thermodynamics brooked no exceptions. The universe was a giant machine that was slowly running down, and nothing could stop it. What Kelvin couldn't have known in 1852 was how much more complex and terrifying the actual process would turn out to be. He envisioned heat death as a relatively quick and straightforward process, perhaps taking place over millions or billions of years. He had no conception of the vast timescales actually involved, no understanding of nuclear fusion, no knowledge of quantum mechanics, and no awareness of the bizarre final stages that modern cosmology has revealed. The real heat death would turn out to be far stranger and far more drawn out than anything Kelvin imagined. But his basic insight was correct. The universe is indeed doomed to reach a state of maximum entropy. The only question was how long it would take and what the journey would look like. When Albert Einstein first encountered Boltzmann's statistical interpretation of thermodynamics, he had a profound objection. If entropy was really just about probability, Einstein reasoned, then the second law wasn't truly a law at all. It was just a statistical tendency. Given enough time, random fluctuations should occasionally cause entropy to decrease, at least temporarily. Einstein's objection led him to one of his most important early contributions to physics, the theory of Brownian motion. By studying the random jiggling of pollen particles suspended in water, Einstein proved that thermal motion at the microscopic level could indeed cause temporary decreases in entropy. The pollen particles would occasionally cluster together purely by chance, creating pockets of order in an otherwise disordered system. But Einstein's work also revealed why these fluctuations didn't violate the second law in any meaningful way. The decreases in entropy were tiny, temporary, and overwhelmingly outnumbered by increases. For every moment when chance created a bit of order, there were billions of moments when chance destroyed far more order. The overall trend was still inexorably toward higher entropy. Moreover, Einstein calculated that the larger the system, the smaller and less frequent these fluctuations became. In a glass of water, you might see tiny temporary clusters of molecules. In a swimming pool, such fluctuations would be undetectable. On the scale of the universe, they would be negligible beyond any possibility of measurement. This work established the foundation of statistical mechanics and revealed the true nature of the second law. It's not an absolute prohibition against entropy decreases. It's a statement about overwhelming probability. Entropy decreases can happen, but they're so rare and so small that they have no practical impact on the universe's overall evolution toward maximum entropy. Einstein's analysis also revealed something beautiful about the relationship between order and chaos. Even in a universe destined for heat death, temporary pockets of order can emerge spontaneously from the underlying chaos. Life itself might be seen as an elaborate version of this phenomenon, complex structures that emerge from simpler components through the interplay of chance and physical law. In 1998, two teams of astronomers set out to measure something that everyone thought they already knew: how fast the universe's expansion was slowing down. The logic seemed unshakable. Gravity pulls everything together, so the expansion that began with the Big Bang must be gradually decelerating as cosmic gravity applies its cosmic brakes. Instead, Saul Perlmutter, Brian Schmidt, Adam Riess, and their teams discovered something that shook the foundations of cosmology. The universe wasn't slowing down, it was speeding up. The expansion was accelerating, driven by a mysterious force that seemed to permeate every cubic centimeter of empty space. They called this force dark energy, and it immediately became the biggest mystery in physics. Whatever dark energy is, it makes up about 68% of the universe, more than all the matter and ordinary energy combined. And its effect is absolutely devastating for the universe's long-term prospects. Dark energy doesn't just make the heat death inevitable, it makes it happen faster and in the most thorough way possible. By accelerating the expansion of space itself, dark energy is actively tearing the universe apart, spreading matter and energy ever thinner, and ensuring that the final state of maximum entropy is reached in the most complete and irreversible way possible. The discovery of dark energy transformed our understanding of cosmic evolution. Previous models had suggested that the universe might eventually contract in a big crunch, potentially recycling its energy and matter for a new cycle of expansion. Dark energy makes this impossible. The universe is locked into eternal expansion, eternal cooling, and eternal dilution of its energy and matter. The most likely explanation for dark energy is what physicists call the cosmological constant, a property of space itself that causes it to expand at an accelerating rate. Einstein first proposed the cosmological constant in 1917 as a way to create a static universe model, but he later abandoned it when Hubble discovered cosmic expansion. He allegedly called it his greatest blunder. If Einstein could see what we know now, he might not be so hard on himself. The cosmological constant appears to be real, and it's the driving force behind the universe's acceleration toward heat death. Every cubic meter of empty space carries a tiny amount of energy density, about 6 times 10 to the negative 10th power joules per cubic meter. This seems negligible, but when multiplied by the vast volume of the universe, it adds up to the dominant component of cosmic energy. What makes dark energy so insidious is that its density remains constant even as space expands. When matter gets diluted by expansion, its density decreases. When radiation gets diluted by expansion, its density decreases even faster due to cosmological redshift. But dark energy's density stays the same. As the universe expands, more dark energy comes into existence, driving even faster expansion, which creates even more dark energy in an endless positive feedback loop. This means that dark energy's dominance over matter and radiation will only increase with time. Today, dark energy makes up about 68% of the universe's energy density. In the future, as matter and radiation become increasingly diluted, dark energy will approach 100% dominance. The universe will become an exponentially expanding void, filled with nothing but the energy of empty space itself. The mathematics of this process are terrifying in their simplicity. The scale factor of the universe grows exponentially. With time, when dark energy dominates, distances between unbound objects increase exponentially. The observable universe shrinks exponentially as light from distant objects can no longer reach us. The cosmic microwave background radiation gets redshifted to longer and longer wavelengths until it becomes undetectable. Eventually, even the most fundamental forces become unable to maintain the coherence of complex structures. One of the most psychologically disturbing consequences of dark energy is what cosmologists call the Great Isolation. As space expands at an accelerating rate, distant galaxies move away from us faster and faster. Eventually, they move away so fast that light from them can never reach us, no matter how long we wait. This is already happening. There are galaxies so distant that we're seeing them as they were billions of years ago, and the light they're emitting right now will never reach us. These galaxies have crossed our cosmic event horizon. They've become causally disconnected from our region of space-time. But the cosmic event horizon isn't static. It's actually shrinking. Galaxies that we can see today will eventually disappear beyond the horizon. Over time, fewer and fewer galaxies will remain visible from our vantage point. The night sky will become progressively emptier and emptier. In about 100 billion years, a timescale that sounds long, but is actually quite short in cosmic terms, our local group of galaxies, the Milky Way, Andromeda, and their smaller companions, will be completely isolated. We'll be able to see the galaxies within our gravitationally bound group, but everything else will have disappeared beyond the cosmic horizon. Any intelligent beings living in our galaxy at that time will have a radically different view of the universe than we do. They'll see a small cluster of galaxies surrounded by empty space. They'll have no evidence of the Big Bang, no cosmic microwave background, no indication that the universe was ever different than it is in their time. They'll think they live in a small static universe, what we might call an island universe. This has profound implications for the nature of scientific knowledge. Truth depends on perspective and timing. The cosmic truth that we can observe today, evidence of the Big Bang, the cosmic web of galaxies, the expansion of space, will be literally invisible to future observers. They'll develop theories and models based on the limited evidence available to them, and those theories will be dramatically wrong by our standards. But from their perspective, working with the data they can access, their theories will be perfectly reasonable. This raises disturbing questions about our own understanding. What crucial evidence about the universe's nature and history has already moved beyond our cosmic horizon? What fundamental truths about reality are we missing because we exist at this particular moment in cosmic history? The expanding universe doesn't just isolate us physically, it isolates us informationally, cutting us off from parts of reality that might hold the keys to understanding existence itself. Dark energy doesn't just isolate galaxies, it gradually shuts down the processes that create new stars. Star formation requires gravity to overcome the outward pressure of gas and radiation, collapsing clouds of hydrogen and helium into dense, hot cores, where nuclear fusion can ignite. But as dark energy spreads matter ever thinner, it becomes increasingly difficult for gravity to accumulate the material needed for new stars. The universe's star formation rate peaked about 10 billion years ago, when galaxies were smaller, denser, and more actively interacting with each other. Since then, star formation has been steadily declining. Today, the rate is only about 3% of its peak value, and thanks to dark energy, this decline will continue until star formation ceases entirely. The process works like this. As space expands, the average density of matter decreases. Lower density means weaker gravitational fields. Weaker gravitational fields make it harder to collapse gas clouds into stars. Meanwhile, existing stars are converting hydrogen into heavier elements and dispersing those elements into space when they die. The primordial hydrogen that fueled the first generation of stars is gradually being consumed and converted into elements that are less efficient nuclear fuel. At the same time, dark energy is accelerating the expansion of space itself, working directly against gravity's attempts to collect matter into star-forming regions. The competition between gravity, trying to pull matter together, and dark energy, trying to push space apart, is gradually being won by dark energy. Current models suggest that star formation will decline by a factor of 10 every billion years. In about 10 billion years, the rate will be so low that only the most massive galaxies will be able to form new stars, and even then, only occasionally. In 100 billion years, star formation will essentially cease throughout the observable universe. This means we're living during the universe's stelliferous era, the brief period when stars shine throughout the cosmos. Before this era, the universe was too young and too hot for stars to form. After this era, the universe will be too old and too diffuse for stars to form. The stelliferous era represents perhaps 0.1% of the universe's total lifespan, and we happen to exist during this infinitesimally brief moment of cosmic illumination. Not all stars die the same way, and understanding the hierarchy of stellar death is crucial to understanding how the universe evolves toward heat death. The most massive stars, those with more than about 25 times the mass of our Sun, live fast and die young in spectacular supernova explosions that can outshine entire galaxies for months. These blue supergiant stars are the universe's gas guzzlers. They burn through their nuclear fuel so quickly that they live for only a few million years, practically an instant on cosmic timescales. When they exhaust their fuel, they undergo catastrophic core collapse, triggering explosions so violent that they can be seen from billions of light years away. But supernovae don't just destroy stars. They also create and distribute the heavy elements that make planets and life possible. The explosion forges elements heavier than iron and blasts them into space, where they eventually become incorporated into new generations of stars and planets. In a sense, massive stars are cosmic alchemists, transmuting simple hydrogen and helium into the complex chemistry needed for rocky planets and biological molecules. However, this process is not perfectly efficient. With each generation of stellar death and rebirth, some material is locked away in stellar remnants, neutron stars, and black holes that remove matter from the active cycle of star formation. Over time, the universe's supply of star-forming material becomes depleted not just through conversion into heavy elements, but through permanent sequestration in compact objects. Medium-mass stars like our Sun follow a different path. They live much longer, about 10 billion years, but they also die more quietly. Instead of exploding, they gradually shed their outer layers as planetary nebulae, while their cores contract into white dwarf stars. White dwarfs are incredibly dense objects. Imagine the mass of the Sun compressed into a sphere the size of Earth. but they're also incredibly stable. Once formed, a white dwarf can persist for hundreds of billions of years, slowly cooling and fading as it radiates away its residual heat. The smallest stars, red dwarfs with less than about 40% of the Sun's mass, are the universe's ultimate survivors. These dim orange stars burn their fuel so efficiently and at such low temperatures that they can continue fusing hydrogen for trillions of years. They'll be the last stars shining when everything else has gone dark. But even red dwarfs must eventually die. They'll spend their final eons as slowly cooling white dwarfs, gradually fading from red to infrared to invisible blackness. When the last red dwarf finally exhausts its fuel and joins the ranks of cooling white dwarf remnants, the stelliferous era will be over. The universe will enter what cosmologists call the Degenerate Era, a time when only stellar corpses remain. At the center of nearly every large galaxy lurks a supermassive black hole, an object containing millions or billions of times the mass of our Sun, compressed into a region smaller than our solar system. These monsters are some of the most efficient engines of entropy production in the universe, converting matter into energy with far greater efficiency than nuclear fusion. When matter falls into a supermassive black hole, it forms an accretion disk that heats up to millions of degrees, glowing brilliantly across the electromagnetic spectrum. The process converts about 10% of the matter's rest mass into radiated energy, far more efficient than the 0.7% efficiency of hydrogen fusion in stars. This energy is then dispersed into space as heat, contributing to the universe's overall entropy increase. But supermassive black holes also play a more subtle role in accelerating the heat death. Through a process called galactic feedback, they regulate star formation in their host galaxies. When a supermassive black hole becomes active, either by accreting matter or by merging with another black hole, it can generate powerful jets and winds that heat up the surrounding gas and prevent it from cooling enough to form new stars. This creates a negative feedback loop that gradually shuts down star formation in mature galaxies. As galaxies age and their central black holes grow larger, they become increasingly effective at suppressing new star formation. This accelerates the transition from the current stelliferous era to the future degenerate era. The growth of supermassive black holes also represents a form of information destruction that contributes to the heat death process. According to the black hole information paradox, information that falls into a black hole may be permanently lost from the universe, representing a form of entropy increase that goes beyond simple energy dissipation. Recent observations have revealed that supermassive black holes were already massive in the early universe. Some existed when the universe was less than 1 billion years old. This suggests that they formed and grew very quickly, possibly from the direct collapse of massive gas clouds in the first galaxies. Their early presence means they've been influencing galactic evolution and star formation for most of cosmic history. While dark energy drives the universe's acceleration toward heat death, dark matter shapes the architecture of that process. Dark matter makes up about 27% of the universe's energy density, 5 times more than ordinary matter, and it forms the invisible scaffolding on which galaxies and galaxy clusters are built. Dark matter particles interact only through gravity, not through electromagnetic forces. This means they can't radiate energy away and cool down like ordinary matter. Instead, dark matter forms vast halos around galaxies and filaments, connecting galaxy clusters, the cosmic web that gives the universe its large-scale structure. But dark energy is gradually destroying this cosmic web. As space expands and matter becomes more diffuse, the gravitational forces holding the cosmic web together become weaker. Dark matter halos expand and become less dense. The filaments connecting galaxy clusters stretch and thin out. Eventually, the cosmic web will be torn apart by the accelerating expansion of space. This process happens gradually at first, then catastrophically. For billions of years, the cosmic web remains intact, while individual galaxies slowly exhaust their star-forming material. But as dark energy's dominance increases, larger and larger structures become gravitationally unbound. First, galaxy clusters break apart. Then, smaller galaxy groups dissolve. Finally, even individual galaxies may be disrupted if dark energy's acceleration becomes extreme enough. The fate of dark matter in the very long term is uncertain. If dark matter particles are their own antiparticles, they might slowly annihilate each other, converting their mass into radiation that gets dispersed by cosmic expansion. If dark matter is stable, it will persist as a thin, invisible component of the universe even after all ordinary matter has been processed through stars and black holes. But regardless of its ultimate fate, dark matter can't prevent the heat death. It might slow down the process by providing additional gravitational binding for structures, but it can't overcome the relentless expansion driven by dark energy. The cosmic web that dark matter helped create will eventually be stretched into invisibility, leaving behind only isolated remnants drifting apart at ever-increasing speeds. One of the most poignant casualties of dark energy's acceleration is the cosmic microwave background, CMB, the afterglow of the Big Bang, that currently bathes the universe in faint radiation at a temperature of 2.7 Kelvin above absolute zero. The CMB is one of our most important sources of information about the early universe, encoding details about the conditions that existed when the universe was only 380,000 years old. But the CMB is not eternal. As space expands, the wavelength of CMB photons gets stretched by cosmological redshift. What started as visible light 13.8 billion years ago has already been redshifted into microwave radiation. As expansion continues, the CMB will be redshifted into infrared, then radio waves, then wavelengths so long that they become undetectable by any conceivable instrument. The accelerating expansion driven by dark energy makes this process happen faster than it would in a universe dominated by matter and radiation. In a matter-dominated universe, the CMB would cool as the inverse of the cosmic scale factor. But in a dark energy-dominated universe, the cooling accelerates as space itself expands exponentially. Current models suggest that the CMB will become undetectable within about 1 trillion years, long before the last stars burn out, but relatively soon in terms of the universe's total lifespan. When this happens, one of the most important sources of information about cosmic history will be lost forever. This represents a profound form of information destruction that contributes to the heat death process. The universe is not just losing energy and becoming more disordered, it's also losing information about its own past. The evidence of the Big Bang, the pattern of initial density fluctuations, the composition of the primordial plasma, all of this information will be stretched into undetectability and effectively erased from the observable universe. The loss of the CMB also has implications for any future civilizations that might arise. They will have access to much less information about the universe's history and structure than we do. Their cosmological theories will be based on incomplete data, and they may reach conclusions about the nature of reality that are fundamentally different from our own, not because they're less intelligent or less capable, but because the universe will have literally erased the evidence they would need to understand their cosmic context. Dark energy may not be the only force accelerating the universe toward its doom. Recent theoretical work in particle physics has revealed an even more catastrophic possibility. The Higgs field that gives particles their mass might not be in its most stable configuration. If the Higgs field exists in what physicists call a false vacuum state, it could spontaneously tunnel to a lower energy state, triggering a bubble of true vacuum that expands at the speed of light and fundamentally rewrites the laws of physics. dark matter particles interact only through gravity, not through electromagnetic forces. This means they can't radiate energy away and cool down like ordinary matter. Instead, dark matter forms vast halos around galaxies and filaments connecting galaxy clusters, the cosmic web that gives the universe its large-scale structure. But dark energy is gradually destroying this cosmic web. As space expands and matter becomes more diffuse, the gravitational forces holding the cosmic web together become weaker. Dark matter halos expand and become less dense. The filaments connecting galaxy clusters stretch and thin out. Eventually, the cosmic web will be torn apart by the accelerating expansion of space. This process happens gradually at first, then catastrophically. For billions of years, the cosmic web remains intact, while individual galaxies slowly exhaust their star-forming material. But as dark energy's dominance increases, larger and larger structures become gravitationally unbound. First, galaxy clusters break apart. Then, smaller galaxy groups dissolve. Finally, even individual galaxies may be disrupted if dark energy's acceleration becomes extreme enough. The fate of dark matter in the very long term is uncertain. If dark matter particles are their own antiparticles, they might slowly annihilate each other, converting their mass into radiation that gets dispersed by cosmic expansion. If dark matter is stable, it will persist as a thin, invisible component of the universe, even after all ordinary matter has been processed through stars and black holes. But regardless of its ultimate fate, dark matter can't prevent the heat death. It might slow down the process by providing additional gravitational binding for structures, but it can't overcome the relentless expansion driven by dark energy. The cosmic web that dark matter helped create will eventually be stretched into invisibility, leaving behind only isolated remnants drifting apart at ever-increasing speeds. One of the most poignant casualties of dark energy's acceleration is the cosmic microwave background, CMB, the afterglow of the Big Bang that currently bathes the universe in faint radiation at a temperature of 2.7 Kelvin, above absolute zero. The CMB is one of our most important sources of information about the early universe, encoding details about the conditions that existed when the universe was only 380,000 years old. But the CMB is not eternal. As space expands, the wavelength of CMB photons gets stretched by cosmological redshift. What started as visible light 13.8 billion years ago has already been redshifted into microwave radiation. As expansion continues, the CMB will be redshifted into infrared, then radio waves, then wavelengths so long that they become undetectable by any conceivable instrument. The accelerating expansion driven by dark energy makes this process happen faster than it would in a universe dominated by matter and radiation. In a matter-dominated universe, the CMB would cool as the inverse of the cosmic scale factor. But in a dark energy-dominated universe, the cooling accelerates as space itself expands exponentially. Current models suggest that the CMB will become undetectable within about 1 trillion years, long before the last stars burn out, but relatively soon in terms of the universe's total lifespan. When this happens, one of the most important sources of information about cosmic history will be lost forever. This represents a profound form of information destruction that contributes to the heat death process. The universe is not just losing energy and becoming more disordered, it's also losing information about its own past. The evidence of the Big Bang, the pattern of initial density fluctuations, the composition of the primordial plasma, all of this information will be stretched into undetectability and effectively erased from the observable universe. The loss of the CMB also has implications for any future civilizations that might arise. They will have access to much less information about the universe's history and structure than we do. Their cosmological theories will be based on incomplete data, and they may reach conclusions about the nature of reality that are fundamentally different from our own, not because they're less intelligent or less capable, but because the universe will have literally erased the evidence they would need to understand their cosmic context. Dark energy may not be the only force accelerating the universe toward its doom. Recent theoretical work in particle physics has revealed an even more catastrophic possibility. The Higgs field that gives particles their mass might not be in its most stable configuration. If the Higgs field exists in what physicists call a false vacuum state, it could spontaneously tunnel to a lower energy state, triggering a bubble of true vacuum that expands at the speed of light and fundamentally rewrites the laws of physics. What happens next is one of the most violent events in the universe: core collapse and supernova explosion. The iron core collapses from the size of the Earth to the size of a city in less than a second, rebounding in a shock wave that tears through the star's outer layers at speeds of 10,000 kilometers per second. The explosion releases more energy in 10 seconds than our sun will produce in its entire 10 billion year lifetime. But supernovae are not just death, they are also birth. The extreme temperatures and densities in the explosion create conditions where elements heavier than iron can be formed through rapid neutron capture processes. Gold, platinum, uranium, and dozens of other heavy elements are forged in these cosmic furnaces and blasted into space, where they will eventually be incorporated into new generations of stars and planets. Stars with masses between about 0.8 and 8 times that of our Sun follow a more sedate path toward their ultimate fate. Our own Sun is a perfect example of this intermediate mass category, and its evolution provides a template for understanding how the majority of the universe's stars will contribute to the heat-death process. Currently, the Sun is in its main sequence phase, steadily fusing hydrogen into helium in its core at a rate of about 600 million tons per second. This process converts approximately 4 million tons of matter into energy every second. In accordance with Einstein's mass-energy equivalence, the energy travels from the core to the surface through a combination of radiation and convection, taking an average of 100,000 years to make the journey before finally escaping into space as sunlight. In about 5 billion years, the Sun will exhaust the hydrogen in its core. Unlike massive stars, it won't be hot or dense enough to immediately begin fusing helium. Instead, hydrogen fusion will continue in a shell surrounding the inert helium core. This shell burning will cause the Sun to expand dramatically, becoming a red giant star with a radius that may extend beyond the orbit of Mars. The red giant phase is a period of instability and mass loss. The Sun's outer layers will become loosely bound, and stellar winds will carry away a significant fraction of the star's mass. These winds will create beautiful but ephemeral planetary nebulae, glowing shells of ionized gas that can be visible from thousands of light years away, but fade within tens of thousands of years. Eventually, the helium core will become hot and dense enough to ignite helium fusion through the triple alpha process, converting helium into carbon and oxygen. This helium burning phase will last only about 100 million years, much shorter than the main sequence hydrogen burning phase. When the helium is exhausted, stars like the Sun lack the mass needed to initiate carbon fusion, so their nuclear evolution ends. The final act of intermediate mass stellar evolution is the formation of a white dwarf, one of the most exotic objects in the universe. When nuclear burning ceases, gravity causes the star's core to contract until it's supported by electron degeneracy pressure. The result is an object with roughly the mass of the Sun compressed into a sphere the size of Earth, with a surface gravity about 100,000 times stronger than Earth's. White dwarfs are incredibly hot when they form. Surface temperatures can exceed 100,000 Kelvin, but they have no internal energy source. They shine only by radiating away, the thermal energy stored in their crystalline cores. This cooling process is extraordinarily slow because white dwarfs have enormous heat capacity but relatively small surface area for radiating energy away. A newly formed white dwarf will spend about 1 billion years cooling from 100,000 Kelvin to 10,000 Kelvin, during which it appears as a blue-white star. It will then spend another 4 billion years cooling to about 5,000 Kelvin, appearing yellow like our Sun. The next phase, cooling from 5,000 Kelvin to 1,000 Kelvin, takes about 50 billion years, longer than the current age of the universe. The final cooling from 1,000 Kelvin to near absolute zero will take hundreds of billions of years. This timeline reveals one of the most important aspects of the heat death process. Even after nuclear burning ceases, the universe will continue to extract energy from stellar remnants for timescales that dwarf the current age of the cosmos. White dwarfs are essentially cosmic storage batteries, holding vast amounts of thermal energy that will be slowly radiated away over hundreds of billions of years. The smallest stars, those with masses between about 0.08 and 0.4 times that of our Sun, represent the universe's ultimate survivors in the face of heat death. These red dwarf stars burn their nuclear fuel so efficiently and at such low rates that they can continue shining for trillions of years, long after all more massive stars have evolved into white dwarfs, neutron stars, or black holes.
But brown dwarfs also illustrate the universe's inefficiency at converting matter into energy. Unlike stars, which can convert about 0.7% of their mass into energy through hydrogen fusion, brown dwarfs can only extract a tiny fraction of their gravitational binding energy, perhaps 0.001% of their mass energy equivalent. The vast majority of their mass energy remains locked up in their constituent particles, inaccessible unless and until those particles undergo more exotic processes like proton decay. The heat death process isn't limited to stars. It also governs the evolution of planetary systems and all solid matter in the universe. Planets, asteroids, comets, and interplanetary dust are all subject to the same inexorable laws of thermodynamics that drive stellar evolution, but their evolution occurs on different timescales and through different mechanisms. Rocky planets like Earth are constantly losing energy through several processes. Radioactive decay of elements like uranium, thorium, and potassium provides heat that gradually escapes through the planet's surface. Tidal interactions with the parent star cause internal friction that dissipates orbital energy as heat. Solar radiation absorbed during the day is re-radiated as infrared radiation at night, contributing to the entropy increase of the universe. On very long timescales, these energy loss mechanisms cause profound changes in planetary systems. Tidal interactions gradually slow planetary rotation and alter orbital characteristics. Earth's rotation is already slowing due to tidal friction with the Moon, and in billions of years, Earth and the Moon will become tidally locked, always showing the same face to each other. The radioactive elements that power planetary geology have limited lifetimes. Uranium-235 has a half-life of 704 million years, so most of it has already decayed since the formation of the solar system. Uranium-238 has a half-life of 4.47 billion years, meaning that about half has decayed since Earth formed. Thorium-232 has a half-life of 14.05 billion years, so it will persist longer. But even it will be largely gone within 100 billion years. As radioactive elements decay away, planets lose their internal heat sources. Geological activity slows and eventually ceases. Volcanic outgassing stops, atmospheric recycling ends, and planetary surfaces become geologically dead. This process has already occurred on smaller bodies like Mars and the Moon, and it will eventually affect all rocky planets. Gas giant planets face their own form of heat death through the slow loss of their atmospheres. Jupiter and Saturn are still contracting from their formation, releasing gravitational energy that keeps them warmer than they would be from solar heating alone. But this contraction is slowing as the planets approach hydrostatic equilibrium, and their internal heat sources will gradually diminish. Over extremely long timescales, trillions of years, even the orbits of planets become unstable due to gravitational perturbations from passing stars and the gradual evaporation of planetary systems through close encounters. Computer simulations suggest that most planetary systems will be disrupted within about 10 to the 15 years, with planets either falling into their parent stars, being ejected into interstellar space, or spiraling into the central star due to gravitational wave radiation. The solid matter that comprises planets and asteroids represents a form of low-entropy organization that will eventually be randomized through various processes. Meteorite impacts gradually break down large bodies into smaller fragments. Solar wind and cosmic rays cause atmospheric erosion and surface weathering. Over geological time, mountains erode, continents drift, and the organized structures of planetary geology give way to increasing disorder. But the most fundamental threat to solid matter comes from the possibility of proton decay. If protons are indeed unstable on very long timescales, as suggested by some grand unified theories, then all atomic nuclei will eventually disintegrate. The carbon, silicon, iron, and other elements that comprise rocky planets will spontaneously decay into lighter particles and energy, causing even the most stable solid structures to literally dissolve. Between the stars lies a tenuous mixture of gas, dust, and cosmic rays known as the interstellar medium, ISAM. Though it contains only about 10% of the galaxy's mass, the ISM plays a crucial role in stellar evolution and the heat death process. It serves as both the raw material for new star formation and the repository for the processed elements ejected by dying stars. The ISM is not uniform but consists of several distinct phases with different temperatures, densities, and compositions. Cold molecular clouds with temperatures of 10 to 20 K serve as stellar nurseries where gravity can overcome thermal pressure to form new stars. Warm neutral hydrogen regions at 8,000 K fill much of the galactic disk. Hot ionized gas at temperatures of 10 to the 6th K has been heated by supernova explosions and stellar winds. This multi-phase structure is maintained by the continuous input of energy from stellar processes. Massive stars heat and ionize surrounding gas through their intense ultraviolet radiation. Stellar winds from all types of stars sweep up and compress the ISM. Supernova explosions inject enormous amounts of kinetic energy, creating hot bubbles and driving large-scale circulation patterns in the galactic gas. But all of these energy sources are gradually declining as the universe ages. The formation rate of massive stars, the primary sources of ISM heating, peaked billions of years ago and continues to decline. As existing massive stars exhaust their fuel and die, fewer remain to maintain the complex thermal structure of the ISM. This has profound implications for future star formation. Cold molecular clouds can only form stars when they're dense enough for gravity to overcome thermal pressure and magnetic field support. As the heating sources diminish, more of the ISM will cool to low temperatures, potentially making star formation more efficient in the short term. However, this cooling process also leads to a fundamental problem: the gradual depletion of gas phase materials. Each generation of star formation converts some of the ISM's gas into stars, and those stars then process the gas through nuclear burning. When the stars die, they return processed material to the ISM. But the total amount of gas available for future star formation continuously decreases. Some gas gets permanently locked up in long-lived stellar remnants like white dwarfs and neutron stars. Other gas gets ejected from the galaxy entirely through galactic winds, driven by supernova explosions and active galactic nuclei. Still more gets consumed by the central supermassive black hole during periods of accretion. The net result is that galaxies gradually exhaust their star-forming fuel. Computer simulations suggest that star formation in galaxies like the Milky Way will decline exponentially with a characteristic timescale of about 4-5 billion years. Within 10-20 billion years, the rate will be so low that only occasional flares of star formation will occur when gas clouds are compressed by galaxy interactions or other disturbances. The ISM also plays a role in the heat death process through its interaction with cosmic rays. High-energy particles accelerated by supernova shock waves and other violent astrophysical processes. Cosmic rays carry significant amounts of energy, but they gradually lose this energy through interactions with ISM gas and magnetic fields. The energy is degraded into heat, contributing to the overall entropy increase of the universe. As the galaxy ages and supernova rates decline, cosmic ray production will also decrease. The high-energy particle population that currently permeates the ISM will gradually lose energy and fade away, eliminating another source of non-thermal energy that helps maintain the ISM's complex structure. On the largest scales, individual galaxies are not isolated systems, but members of complex gravitational hierarchies that extend from small groups to massive clusters containing thousands of galaxies. These gravitational interactions play a crucial role in accelerating some aspects of stellar evolution, while slowing others, ultimately affecting the timeline of the heat death process. Galaxy mergers are among the most dramatic events in cosmic evolution. When two large galaxies approach each other, their gravitational interaction triggers bursts of star formation as gas clouds are compressed and destabilized. The merger also feeds the central supermassive black holes, leading to periods of intense quasar activity that can temporarily outshine all the stars in both galaxies combined. Our own Milky Way galaxy is destined to merge with the Andromeda galaxy in approximately 4.5 billion years. Computer simulations show that this collision will reshape both galaxies, likely forming a single elliptical galaxy that astronomers have nicknamed Milkomeda. The merger will trigger intense star formation that could consume much of the remaining gas in both galaxies within a few billion years. But galaxy mergers also demonstrate the universe's evolution toward heat death through gravitational interactions. During a merger, stars are scattered into new orbits through a process called violent relaxation. Some stars gain energy and are ejected into intergalactic space, while others lose energy and sink toward the center of the merged galaxy. This process increases the entropy of the stellar distribution, creating a more randomized configuration. The ejected stars become isolated wanderers in the expanding universe. Cut off from the galaxy's remaining gas supply, they can never participate in future star formation. They're condemned to evolve in isolation, gradually exhausting their nuclear fuel and fading into darkness without contributing to any cosmic recycling processes. Meanwhile, the stars that sink toward the galactic center face their own grim fate. As they crowd into the central regions, their orbits become increasingly chaotic due to gravitational perturbations from neighboring stars. Some will be tidally disrupted by close encounters with the central supermassive black hole. Others will be flung out of the galaxy entirely through gravitational slingshot effects. The end result of galaxy evolution is a gradual expansion and dispersal of stellar orbits. What begins as an organized spiral or elliptical galaxy slowly evolves into a more extended, less structured system. The process is irreversible. Once stars are scattered into extended orbits, they cannot spontaneously reassemble into a compact galaxy. This stellar evaporation process operates on timescales of 10 to the 11 to 10 to the 12 years for typical galaxies. By the time the last red dwarf stars are exhausting their nuclear fuel, most galaxies will have lost a significant fraction of their stellar mass to intergalactic space. The remaining stars will be distributed over volumes much larger than present-day galaxies, making gravitational interactions increasingly rare. Galaxy clusters, the largest gravitationally bound structures in the universe, face a similar fate through a process called evaporation. Galaxies within clusters have a distribution of velocities, and occasionally a galaxy will gain enough energy through gravitational interactions to escape the cluster entirely. Over time, this process causes clusters to gradually lose mass and become less tightly bound. The expansion of space driven by dark energy accelerates this evaporation process by weakening the gravitational binding of large structures. Clusters that are marginally bound today will become unbound as space expands, and their internal velocities carry member galaxies beyond the escape velocity. Magnetic fields permeate space at every scale, from individual stars to entire galaxy clusters, and they play a subtle but important role in the heat-death process. These fields carry energy that must ultimately be dissipated as heat, contributing to the universe's entropy increase, while also affecting the timescales and mechanisms of stellar and galactic evolution.
Stellar magnetic fields are generated by dynamo processes in the convective zones of stars. The Sun's magnetic field undergoes an 11-year cycle of reversals, creating sunspots, solar flares, and coronal mass ejections that carry magnetic energy away from the star. This energy is ultimately converted to heat when the magnetic plasma interacts with the interstellar medium. More dramatically, some stars have magnetic fields thousands of times stronger than the Sun's. These magnetic stars lose rotational energy through magnetic braking. The magnetic field couples to the stellar wind, creating a torque that slows the star's rotation. The lost rotational energy is carried away as magnetic energy in the wind and eventually dissipated as heat. The most extreme magnetic objects are neutron stars, particularly those known as magnetars. These ultra-dense stellar remnants can have magnetic fields trillions of times stronger than Earth's. The magnetic field energy in a magnetar can exceed the binding energy of the star itself, making these objects incredibly unstable and prone to violent outbursts. Magnetars undergo magnetic field decay on timescales of thousands to millions of years. As the field decays, its energy is converted to heat and high-energy radiation. A single magnetar flare can release more energy in a few seconds than the Sun produces in a year, representing a rapid conversion of organized magnetic energy into thermal radiation. On larger scales, galaxies possess magnetic fields that thread through the interstellar medium and help regulate star formation. These galactic magnetic fields are maintained by dynamo processes involving the differential rotations of the galactic disk and convective motions in the ISM. Like stellar fields, they represent a form of organized energy that gradually dissipates over cosmic time. The galactic magnetic field affects star formation by providing additional pressure that must be overcome for gas clouds to collapse. It also influences the propagation of cosmic rays, creating magnetic confinement that keeps high-energy particles trapped within the galaxy for longer periods. But magnetic fields also facilitate energy dissipation through magnetic reconnection events and turbulent cascade processes that convert large-scale magnetic energy into heat. Galaxy clusters possess the largest magnetic structures in the universe, field lines that extend across millions of light years and contain energy equivalent to the mass energy of entire stars. These cluster-scale magnetic fields are thought to be generated and maintained by the motion of galaxies through the intracluster medium, but they too are subject to dissipation through various magnetohydrodynamic processes. All of these magnetic phenomena contribute to the heat-death process by providing additional channels for converting organized energy into random thermal motion. Magnetic field energy represents a form of low-entropy configuration that inevitably decays into high-entropy heat, accelerating the universe's evolution toward maximum entropy. The decay of magnetic fields also affects the long-term evolution of cosmic structures. As stellar magnetic fields weaken, stars lose their ability to drive strong stellar winds, potentially extending their lifetimes, but reducing their to enrich the interstellar medium with processed elements. As galactic magnetic fields decay, cosmic ray confinement becomes less effective, allowing high-energy particles to escape more easily and reducing the pressure support that helps maintain the ISM's multiphase structure. In approximately 100 trillion years, a time span 10,000 times longer than the current age of the universe, the last red dwarf star will exhaust its nuclear fuel and fade into darkness. This moment marks the end of the stelliferous era and the beginning of the degenerate era, when the universe will be populated only by stellar remnants, white dwarfs, neutron stars, black holes, and the slowly cooling brown dwarfs that never achieved true stellar status. The transition will not be sudden. For billions of years before the last red dwarf dies, star formation will have essentially ceased as galaxies exhaust their gas supplies and dark energy spreads matter too thin for gravitational collapse. The universe will gradually dim as fewer and fewer nuclear furnaces remain active, until only the feeblest red dwarfs continue to shine with the luminosity of a dim light bulb. When the final red dwarf flickers out, the universe will enter a state fundamentally different from anything in its previous history. For the first time since the Big Bang, there will be no nuclear energy sources anywhere in the cosmos. The only energy available will be the thermal energy stored in cooling stellar remnants, the kinetic energy of particles in motion, and the gravitational potential energy of bound systems. Yet the degenerate era will not be a time of complete darkness. White dwarf stars, the compressed cores of dead sun-like stars, will continue to glow for hundreds of billions of additional years as they slowly radiate away their stored thermal energy. These stellar diamonds, with masses comparable to the Sun, but sizes comparable to Earth, will serve as the primary light sources in a universe that has otherwise gone cold. The landscape of the degenerate era will be hauntingly sparse, where once galaxies contained hundreds of billions of stars, arranged in elegant spiral arms or smooth elliptical distributions, there will instead be vast collections of isolated stellar corpses drifting through an ever-expanding void. The average distance between these remnants will be measured not in light years, as stellar separations are today, but in hundreds or thousands of light years. This enormous increase in the typical distance between objects reflects both the exhaustion of star-forming material and the continued expansion of space driven by dark energy. Galaxies will have expanded to many times their current size, with their constituent stellar remnants following highly elongated orbits that carry them far from the galactic center, before bringing them back in gravitational cycles lasting billions of years. The few surviving planets will have long since been stripped from their parent stars during the chaotic final phases of stellar evolution, or ejected into interstellar space during galaxy mergers and close encounters. These rogue planets will wander through the cosmos as frozen, lifeless worlds, gradually cooling toward the temperature of the cosmic microwave background, which itself will have cooled to a fraction of a degree above absolute zero due to cosmic expansion. White dwarfs represent one of the most fascinating laboratories for studying matter under extreme conditions, and their cooling process provides crucial insights into how the universe will evolve during the degenerate era. These objects contain roughly the mass of our Sun, compressed into a sphere the size of Earth, resulting in densities about 1,000,000 times greater than any material found on Earth. The extreme density of white dwarf material creates physical conditions that have no terrestrial analog. A teaspoon of white dwarf matter would weigh about 5 tons. The gravitational field at the surface is roughly 100,000 times stronger than Earth's gravity. Under these conditions, ordinary matter behaves in ways that seem almost magical compared to our everyday experience. White dwarfs are supported against further gravitational collapse by electron degeneracy pressure, a quantum mechanical phenomenon that prevents electrons from occupying the same quantum state. As electrons are squeezed into smaller and smaller volumes, they must occupy higher and higher energy levels, creating an outward pressure that can balance the inward pull of gravity. This quantum mechanical support mechanism means that white dwarfs don't contract significantly as they cool, unlike normal stars that shrink as they lose energy. Instead, they maintain roughly constant size, while their internal temperature slowly decreases. This creates a unique cooling process that can be calculated precisely using the physics of degenerate matter and thermal conduction. A newly formed white dwarf has an internal temperature of roughly 100 million Kelvin, hot enough for nuclear reactions, but lacking the fuel to sustain them. This thermal energy was deposited during the violent final phases of stellar evolution, when the star's outer layers were ejected and its core was compressed to white dwarf densities. The cooling process begins immediately, driven by the emission of thermal radiation from the white dwarf's surface. However, the rate of cooling is controlled by the thermal conductivity of the white dwarf interior and the heat capacity of the degenerate electron gas. Both of these properties can be calculated from first principles, using quantum statistical mechanics. For the first billion years after formation, a typical white dwarf cools relatively quickly, dropping from surface temperatures of 50,000 to 100,000 Kelvin to about 10,000 Kelvin. During this phase, the white dwarf appears blue-white in color and has a luminosity comparable to a faint main sequence star. But as the white dwarf continues to cool, the process slows dramatically. The thermal conductivity of degenerate matter decreases as temperature drops, creating better insulation that retards further cooling. At the same time, the heat capacity increases, meaning more energy must be removed to produce a given temperature decrease. The result is a cooling curve that flattens significantly after the first few billion years. A white dwarf takes about 5 billion years to cool from 10,000 Kelvin to 5,000 Kelvin, roughly the temperature of the sun's surface. But cooling from 5,000 Kelvin to 2,500 Kelvin takes about 15 billion years, and cooling from 2,500 Kelvin to 1,250 Kelvin takes nearly 50 billion years. This dramatic slowing of the cooling process means that white dwarfs will remain visible sources of thermal radiation for timescales that dwarf the current age of the universe. Even after 100 billion years, when the last red dwarf stars have died, most white dwarfs will still have surface temperatures of several thousand Kelvin, making them among the brightest objects in the night sky of the Degenerate Era. As white dwarfs cool below about 10,000 Kelvin, they undergo one of the most remarkable phase transitions in astrophysics. Their interiors begin to crystallize. The carbon and oxygen nuclei that comprise the bulk of a white dwarf's mass arrange themselves into a crystal lattice structure, transforming the stellar remnant from a hot liquid into a giant cosmic diamond. This crystallization process releases latent heat, just as water releases heat when it freezes into ice, providing an additional energy source that temporarily slows the white dwarf's cooling. The amount of energy released during crystallization is substantial, roughly equivalent to the total energy output of the white dwarf over several billion years of cooling. The crystallization doesn't happen all at once, but proceeds from the center outward over billions of years. As the core temperature drops below the crystallization threshold, carbon and oxygen nuclei begin arranging themselves into the most thermodynamically favorable crystal structure, a body-centered cubic lattice for the mixed carbon-oxygen composition typical of most white dwarfs. This process creates what is essentially a planet-sized diamond with a mass comparable to our Sun. The crystal structure is incredibly pure and regular, with defects and impurities rare due to the extreme conditions that favor perfect ordering. The resulting material has thermal and mechanical properties unlike anything that exists naturally elsewhere in the universe. Crystallized white dwarfs represent a new phase of matter organization in the universe, highly ordered structures that emerge spontaneously from the cooling process. In thermodynamic terms, the crystallization reduces the entropy of the white dwarf's interior, temporarily reversing the local trend toward maximum disorder. However, this entropy decrease is more than compensated by the heat radiated away during the crystallization process, ensuring that the second law of thermodynamics is not violated. The existence of crystallized white dwarfs also has implications for the very long-term evolution of matter in the universe. These cosmic diamonds are incredibly stable structures that could potentially persist for timescales approaching the age of proton decay, 10 to the 34th power years or more. They represent repositories of organized matter that will resist the general trend toward increasing entropy for longer than almost any other structures in the cosmos. But even crystallized white dwarfs must eventually succumb to the heat death. As they continue to cool toward absolute zero, they will radiate away all their remaining thermal energy. The crystal lattice will approach its ground state, with atomic nuclei locked into perfect geometric arrangements separated by the minimum possible distances allowed by quantum mechanics. At this point, the white dwarf will have become what physicists call a black dwarf, a cold, dark, crystalline remnant that emits no detectable radiation. These objects will be among the most long-lived structures in the universe, potentially persisting unchanged for 10 to the power of 32 years or more, until proton decay finally causes their constituent nuclei to disintegrate. At these incredible densities, atomic nuclei are crushed together so tightly that protons and electrons combine to form neutrons. The entire star becomes essentially a single giant atomic nucleus composed almost entirely of neutrons, held together by the strong nuclear force and supported against gravitational collapse by neutron degeneracy pressure. The physics of neutron star interiors involves some of the most extreme conditions in the universe. Pressures in the core can exceed the pressure at the center of atomic nuclei by factors of 10 or more. Under these conditions, matter may exist in exotic phases that cannot be replicated in terrestrial laboratories. Strange quark matter, kaon condensates, or even more exotic forms of matter predicted by quantum chromodynamics. Neutron stars are born rotating rapidly, up to 700 times per second, due to the conservation of angular momentum during the core collapse process. As they age, they gradually slow down by radiating energy in several forms: magnetic dipole radiation, gravitational waves from any asymmetries in their shape, and particle winds that carry away rotational energy. This rotational energy represents a significant energy reservoir that contributes to the heat death process. A typical neutron star contains about 10 to the 42nd power joules of rotational energy when newly formed, roughly equivalent to the total energy output of our Sun over 100 million years. As the neutron star spins down, this energy is gradually converted to electromagnetic radiation and particle kinetic energy, ultimately becoming heat that increases the universe's total entropy. The magnetic fields of neutron stars are among the strongest in the universe, typically 10 to the 8th to 10 to the 12th times stronger than Earth's magnetic field. The most magnetic neutron stars, called magnetars, can have field strengths approaching 10 to the 15th Gauss, so strong that the magnetic energy density exceeds the energy density of matter itself. These intense magnetic fields represent another form of organized energy that must eventually dissipate through various processes. Magnetic field decay in neutron stars occurs through a combination of ohmic dissipation in the stellar crust and magnetic reconnection events that convert field energy into heat and high-energy particles. The timescale for magnetic field decay ranges from thousands to millions of years, depending on the initial field strength and the conductivity of the neutron star material. As neutron stars age and their rotation slows, they become increasingly difficult to detect. Young neutron stars often appear as pulsars, lighthouse-like beams of radiation that sweep across space as the star rotates. But as the rotation rate decreases and the magnetic field weakens, the pulsar mechanism eventually shuts down, leaving behind a dim, slowly rotating neutron star that emits only weak thermal radiation. During the Degenerate Era, neutron stars will be among the faintest objects in the universe. With surface temperatures of only a few degrees above absolute zero and negligible luminosities, they will be essentially invisible except through their gravitational effects. They will persist as ultra-compact, ultra-dense relics of stellar evolution, slowly cooling toward the temperature of the cosmic background radiation. The cooling process for neutron stars follows a complex pattern determined by the physics of dense nuclear matter. Initially, cooling is dominated by neutrino emission from various processes in the hot neutron star interior. Neutrinos interact so weakly with matter that they can escape directly from the stellar core, carrying away enormous amounts of energy and causing rapid cooling during the first million years. After the neutrino cooling phase ends, thermal conduction through the neutron star crust becomes the limiting factor for further cooling. The crust consists of atomic nuclei arranged in a crystalline lattice, immersed in a sea of degenerate electrons and neutrons. This material has extremely high thermal conductivity, allowing heat to flow readily from the interior to the surface. Eventually, neutron stars will cool to the point where their surface temperatures match the cosmic microwave background radiation. At this point, they will be in thermal equilibrium with the universe and will cease to radiate energy away. They will remain at this temperature as the cosmic background radiation continues to cool due to cosmic expansion, following the temperature of the universe itself toward absolute zero. Black holes represent the most extreme manifestation of gravity's triumph over all other forces, and they play a crucial role in the universe's evolution toward heat death. These objects are characterized by event horizons, boundaries in space-time beyond which nothing, not even light, can escape. Everything that crosses an event horizon is doomed to fall toward the central singularity, where the laws of physics as we understand them break down completely. The formation of black holes represents one of the most efficient processes for increasing entropy in the universe. When matter falls into a black hole, it releases gravitational potential energy at an efficiency that can approach 42% for rotating black holes, far exceeding the 0.7% efficiency of nuclear fusion in stars. This energy is radiated away as heat, contributing directly to the universe's entropy increase, while the infalling matter disappears behind the event horizon. But black holes are not perfectly black. In 1975, Stephen Hawking made one of the most profound discoveries in theoretical physics. Black holes actually radiate energy through quantum mechanical processes near their event horizons. This Hawking radiation means that all black holes are slowly evaporating, converting their mass back into energy and particles over incredibly long timescales. The evaporation rate is inversely proportional to the black hole's mass squared. Stellar mass black holes with masses around 10 times that of our Sun will take approximately 10 to the 67th power years to evaporate completely. Supermassive black holes with billions of solar masses will persist for 10 to the power of 100 years or more. But eventually, even these cosmic monsters must succumb to Hawking radiation. As the Degenerate Era draws to a close, after 10 to the 40 years, the last stellar mass black holes will enter their final death spirals. The evaporation process accelerates dramatically As black holes shrink, the smaller they become, the faster they radiate energy. In the final second of a black hole's existence, it releases energy equivalent to billions of hydrogen bombs in a spectacular final flash. When the last black hole evaporates around 10 to the 100 years from now, the universe will enter its final age, the Dark Era. This will be a realm of unimaginable emptiness and cold, where the temperature approaches absolute zero and the average density falls to less than 1 elementary particle per volume, larger than our current observable universe. In the Dark Era, the universe will have reached maximum entropy, the ultimate heat-death state. No temperature gradients will remain to drive any form of work or organization. No nuclear reactions, no chemical processes, no biological metabolism will be possible. Time itself may lose meaning in a universe where nothing ever changes, and no events mark the passage of moments. But even in this seemingly final state, quantum mechanics suggests that the story may not be over. Given infinite time, quantum fluctuations must occasionally create temporary decreases in entropy. In 10 to the power of 56 years, random fluctuations might spontaneously assemble a perfect copy of your brain, complete with all your memories, floating momentarily in the void, before dissolving back into chaos. In 10 to the power of 120 years, fluctuations might create an entire universe identical to our own. Every star, every planet, every person who ever lived would be recreated exactly as they were, living identical lives in an endless cycle of cosmic resurrection and dissolution. So here we stand, 13.8 billion years after the Big Bang, living in the universe's brief golden age, when stars still shine and complexity can flourish. We are witnesses to the greatest story ever told, the cosmos's journey from perfect order to perfect disorder, from the infinite potential of the Big Bang to the infinite stillness of heat death. The heat death of everything is not just inevitable, it's already begun. Every star that's ever burned, every life that's ever lived, every thought that's ever been conceived has contributed to the universe's inexorable march toward maximum entropy. We are entropy's children, born from chaos, destined to return to chaos, yet somehow capable of understanding our cosmic context and finding beauty in our temporary existence. The universe may be doomed, but it is not yet dead. Between now and heat, death lies a time span so vast that entire cosmological ages will rise and fall. Civilizations could spread across galaxies, consciousness could transcend biology, and new forms of complexity could emerge that we cannot imagine. The very fact that matter organized itself into structures capable of contemplating their own fate is perhaps the most remarkable victory over entropy ever achieved. In the end, the heat death reveals both the ultimate futility and the ultimate preciousness of existence. Nothing lasts forever, but everything that exists does so in defiance of the universe's drive toward chaos. Every moment of consciousness, every act of creation, every instance of love represents a temporary triumph of order over disorder, meaning over meaninglessness. The universe is dying, but right now, right here, it is also magnificently, impossibly, gloriously alive, and that makes all the difference.